All right, here I am for some more antenna theory. I'm not a big fan of social media pictures that make it look like everything is great and I'm having way more fun than you, so I took some little candid photos of what's happening at my house right now. There's my son Peter, recently returned from a mission in Japan, chilling in his room. My daughter Amy, in our family, we like to be very positive, so I just refer to her as unique. And Sister Warnick, who is sewing something. So that gives you an idea of what's happening here. Meanwhile, I am talking about spherical waves. So what we're doing is really an application of the far-field radiation integral. We developed Green's functions, we looked at the magnetic vector potential, and all of that was mathematical or theoretical machinery aimed at creating this expression, which is what we use to find fields radiated by antennas. We start with a current model, then we work an integral, which is a three-dimensional Fourier transform. Then we add a spherical wave term. We adjust the vector direction, multiply by constant, and that gives us the output, which is the field radiated by the antenna. And from that, we can find antenna parameters, which we're going to look at in just a minute. What is it that is important about the performance of an antenna? So, since this is our main mathematical tool for antenna theory, we need to spend a little bit of time sort of dwelling on this expression and trying to understand it. The first term, starting from the right, is an integral e to the j k r hat dot r prime, j of r prime, dr prime, and that's a Fourier transform. That means that there's a Fourier relationship between the current that represents an antenna and the fields that it radiates. What we're integrating out of the transform is r prime. So r prime is gone, and what's left is r hat. Now r hat, we often will write in a combination of spherical and rectangular coordinates. We write that in the form sine theta cosine phi x hat plus sine theta sine phi y hat plus cosine theta z hat. Now you can see that r hat is a function of two variables, theta and phi. So after we work this three-dimensional Fourier transform, what's left is the angular dependence of the field radiated by an antenna. So let me just summarize that up here. When we're done working that integral, we have something that depends on theta and phi. That dictates where the energy goes. Now, look at the properties of the Fourier transform. If I have a short impulse in time that has a very broad frequency content in the Fourier domain. Likewise, if I have a small antenna, its radiation pattern tends to be very broad in angle. If I have a very large antenna, like a dish, that's big in the as far as the current, and when we take the three-dimensional Fourier transform, we get an antenna pattern that is very narrow in angle, so most of the energy is directive. So small antenna equals a wide radiation pattern, large antenna means a narrow radiation pattern, and that comes from our understandings of Fourier transforms. The next term, moving left, is e to the minus jkr over 4 pi r. And please don't forget that I use little r and big R interchangeably, just two different notations for the same thing. This is a spherical wave. Now, a spherical wave is much like a plane wave, except the phase fronts are not planes, they're spheres. So a spherical wave radiates outward radially away from the origin. Now, unlike a plane wave, the spherical wave changes in amplitude. That 4 pi r causes the field to decay in such a way that power is conserved. If I take the square of that, I'll get a 1 over r squared, and that is proportional to power density, and that precisely matches the increase in area of a sphere. The area of a sphere is 4 pi r squared. So if we think about this 1 over r, that's exactly what we need in the electric field, so that when we square it and integrate over a sphere, power is conserved. No matter how big that sphere gets, the same amount of power crosses the sphere that surrounds an antenna. Now the 1 minus r hat term, it's a little bit of a pain to evaluate sometimes, but it's really quite important. This adjusts the vector direction of the fields. The 1 minus r hat, what it really does operationally is it takes everything to the right of that term and gets rid of the r hat component. So when I work the integral in that first term on the far right, I would get an r hat times some function and a theta hat times some function, just representing that quantity in spherical unit vectors. Well, when I multiply that by 1 minus r hat, what that does is cancel out the theta hat and phi component, and the r hat component, leaving only the theta and phi components. And that's really important. No matter what the antenna is, whether a little thing or a big dish, it doesn't really matter what the antenna is. Boy, that's a terrible dish. When we get far away from the antenna, the electric and magnetic field are always orthogonal to, this is E and that's H, the r hat direction. So if I think of a sphere around that antenna, the E and the H are always tangential to that sphere, and the radial direction is normal. That's an interesting property of spherical waves. A lot like plane waves in that respect. That means a spherical wave is transverse in the same way that a plane wave is transverse. Okay, and then the minus j omega mu just adjusts the constants, and a little trick that we sometimes use. If I look at omega mu and I compare that to k eta, so k eta is omega squared of mu epsilon, and square root of mu over epsilon. If I combine that, I get omega mu. So sometimes we use omega mu and k eta interchangeably just to simplify expressions. So that's a little guided tour into the far-field radiation integral. Now we're going to go back and look in a little more detail at the far fields of the Hertzian dipole just to round this out. So here I've taken from the lecture notes expressions for the far electric field and the far magnetic field a distance away from the Hertzian dipole. And the next thing I'm going to do is I'm going to find the time average power density. So S average, that's 1/2 real E cross H conjugate. Now I'm going to get the 1/2. The cross product is going to be theta hat cross phi hat. That happens to be r hat. And then I'm going to get the eta, and then I'm going to get in both the E and the H an I naught L K, and then a 4 pi R. I'll write that a little r, even though it's big R up above, squared sine squared theta. And that is the power density radiated by the Hertzian dipole. Now, it's interesting to kind of compare that to what we get for a different antenna. The Hertzian dipole is very, very simple, very approximate. It's just a rough model for a basic antenna. Real antennas are more complicated. What will change about this expression? Well, all antennas will have an R hat, no matter how big the antenna is, how small it is, how complicated it is. The power always goes out radially. So if I draw a generic symbol for the antenna, power always goes out in the R hat direction. Okay, and then the antenna, depending on the type of the antenna, these constants may change. That's dependent on the antenna. But the 1 over r squared, when we take that 1 over r and then square it, that's common to all antennas. No matter what the antenna is, the power always falls off as 1 over r squared, and that's based on conservation of energy. Now the other thing is we have here a function of angle. Now the Hertzian dipole is really simple, so I only have a function of theta, but for more complicated antenna, I could have a function of theta and phi there, and that we call radiation pattern of the antenna. Okay, so we can think of the Hertzian dipole as kind of a simpler version of more complicated antennas. All that would change is the coefficients and the function of angle. And we're going to look at those in the next section of material in terms of antenna parameters.